Hi, this talk is about solving SDP programs with a new flavor of cutting planes called projective cutting planes. It's not related to an orthogonal projection, but it's related to a different operation. We are in a cutting planes framework, but let's say in the very beginning I have zero constraints, uncharted territory. We start from the origin, let's say it's feasible, and we follow the objective function b so as to increase as rapidly as possible the objective. This is the non-orthogonal projection. Imagine that the point where I stay here, it's the origin, and I shoot a bullet into the walls of this room. The place where the bullet will stop, it's a first hit point. I move from y1 to t1 star d1, so the step length is t1. And I also identify the wall where the bullet will stop. In our case, it will be a first hit eigenvector cut. That will help me determine a first outer approximation P1. Its optimal solution is called opt P1 here at the right. Now, my goal is to cut the gap between the outer solution and the feasible set of solutions which stay between this guy and this guy. Let's take some guy in the middle, and let me shoot towards the outer solution. Like you see in the figure, this will identify a new eigenvector cut or a new facet of my room if you want. A new point, a new feasible point, a new outer point. I repeat the operation and I will separate the outer point by projecting. I already found y1, y2, y3 which are interior solutions. And let me now project towards opt P3, and at this point you see that the gap between, if you want, the green guy here, which is an interior solution, and the red lady, if you want, which is beyond the border of feasibility, she is unreachable, but yet by projection we are very, very close. And if we were to do another iteration, I should go to very small details here. I could find here new cutting planes. The red lady would move, maybe follow my mouse around here, and the new iteration will greatly decrease the gap. This is important because if I were to use the standard cutting planes in such area, this is what may easily happen. I have here an instance with dense matrices of strictly positive eigenvalues. The standard cutting planes may need up to almost 10 seconds and spend 9 seconds out of 10, a huge amount of time, only to prove that the outer solution from some point on is optimal. This is even more difficult if there are multiple outer solutions. But you can see here that the new method has both lower and upper bounds, and by closing the gap here we can more easily stop the method. Let's present the problem. This is well known in SDP optimization. Okay, I maximize the linear function over this SDP constraint. This is what we call the dual. Very often it's more interesting to work on the dual because the number of variables in my model will be k, while if I were to work on the primal variables of size n times n, I should handle much more variables, generally speaking. But everything I present here can also be applied on the dual of this program, which is what we often call the primal SDP program in other papers. Don't forget, let me say, we have an LP part, some constraints here which are purely LP, and the SDP constraint is equivalent to inserting an eigenvector cut for each vector in R power n. So if I rewrite the program this way, I forget to some extent about the SDP constraint. I have a number of linear constraints here, it's a polytope, but I have an infinite number of eigenvector cuts. But if I reduce R power n to some finite subset, I obtain a polytope. We could address the problem by separating at each iteration some infeasible solution by finding the minimum eigenvalue of this matrix. Such standard cutting planes is not considered very successful, but people did try very interesting things around it. I hope the new method is better, but it surely needs more work. The most difficulty to solve the non-orthogonal projection. I won't cover it in this very short video, but I also have on the same web page a second video where I do cover it. We also need a first feasible solution to start the method, and any initial linear constraint can be useful. Let's move to point 3, which is the easiest one to cover. What do I want? I want a linear constraint in variable y, which will certify me this relation. I can simply ask the diagonal of this matrix to be non-negative. Of course I do that, but it's not enough. I want another interesting constraint that will certify me this second relation. I use this inequality, which is not very difficult to prove. And what happens? As long as y is non-negative, we will notice using this Veil's inequality that this yellow guy is greater than equal than this decomposed green guy, where I simply replace the overall lambda mean operator that here it's applied on the whole sum of matrices. I distribute it over each element of the sum, if you want. So this is the final linear constraint I can safely insert in my SDP program. Why? If this guy is positive, since this yellow guy is even bigger, this will surely certify me that this relation is satisfied, which means y is feasible with relation to the SDP constraint. I also need an SDP feasible heuristic. Let's take first the optimal y over all the linear constraints you can see here. Such y may violate the SDP constraint, otherwise is the optimal solution of the problem. This means there is an eigenvector v associated to a negative eigenvalue lambda minus of x. Okay, I have this relation that I display it again here. What can I do now? What happens if I move from y towards some y plus d? I define for this purpose a function in which I take the same relation, but I replace yi by yi plus di, and f0 it's the same value as this one, lambda minus, and f is linear in d. Let me find the maximum of f over all d in a small hypercube around 0, still enforcing the linear constraints. This is a standard LP. If this maximum of the standard LP is above lambda minus, this means I can move from y to y plus d and improve the minimum eigenvalue. Modulo some technical details, this is very often the case. And now let me give an idea of if you want the spirit of this technique. If there is somewhere a feasible solution y that satisfies the SDP constraint, this means that this guy has to be non-negative. So by moving from y towards y star, I need to also increase the value of f. And I increase the value of f even if I don't move to that point by a full step, but also if I move by a small step, because everything is linear. I cannot compete with Mosaic on sparse instances from public benchmark. If they have kn and the number of LP cuts around 1000, it solves in 3 minutes thanks to huge work in sparsity. But let me densify an instance. Let me take some orthonormal m. You can check that if I replace hi by this value and the same for c, I keep the same instance. I have strictly the same feasible area, so it's actually the same instance, but Mosaic starts suffering, and the new method, it also suffers. It's more or less the same time as for the sparse variant, but I can hope to compete with Mosaic. And more interestingly, to some extent, I almost don't even need numerical results to address an interesting feature, reoptimizing SDP programs. I've often seen talks where the goal is to solve a sequence of SDP programs. They can differ from one another, for instance, by some branch and bound decision. By implementing the robustness over the LP part, which means that each linear constraint, if you want, in the LP part can explode to an infinite number of other linear constraints which are motivated by, for instance, by errors in physical measurements. The coefficients here can represent some physical measurements. It's a huge robustness theory on LP, but I can have here a program which has an infinite number of constraints for two reasons. One, the SDP part. Secondly, the robust part. The new framework can take them into account at the same time. I mean, into the same framework, I can add at each iteration one cut because of the SDP part and one cut because of the robustness in the same algorithm at the same time. While if I use a standard SDP solver, I need to call the solver multiple times because I cannot serve to Mosaic a robust program for the linear part this way. Conclusion: the new approach can will construct a sequence of inner solutions that do not exist in other cutting planes for SDP programming. They only compute outer solutions, really, to the best of my knowledge. Actually, it generates both a primal and a dual SDP solution. It can be proven quite easily at each iteration, which is something an interior point method cannot do. If an interior point method needs 10 hours to solve a problem, if you can't wait 10 hours, you have nothing, which is not the case for the new method. And finally, this work is actually motivated by the idea that other methods, interior point methods, can run out of gas from a certain value of n because of huge Schur complement matrices to be computed. And if the projection subproblem can be solved quite easily, even for large values of n, if k is quite small, the new method can represent serious competition. I can hope so. Bye bye.